Hello, hello. Are we good? Okay.
Hello.
So, yeah, we're good. Okay. So my name is Miguel Lavalle, and I work with Huawei. And my colleague here is?
I'm Swami, so I'm the DVR guy, so I'm here to help my goal to sort out some issues with router networks with respect to DVR. I'm working for SUSE.
So this is our agenda for today. We are going to talk about the motivation for routed networks. And then we are going to talk about some of the details of routed networks implementation. This presentation was already given a year ago in Barcelona. Some of this presentation. So really, the emphasis that we are going to place here is in the new functionality that we are adding to routed networks, which is floating IPs and how that is going to work with DVR. If we have time at the end, we are going to cover also the interaction with the node scheduler if we have time, and some of the configuration details. So why routed networks? The important thing to remember about Neutron is that, in principle, all your networks in Neutron are a single broadcast domain. The networks are defined at level 2, and they represent a unified broadcast domain. And that, over the time, has allowed us in Neutron to provide a rich toolkit to create complex networking topologies. Really, one of the motivations of the Neutron project, of the OpenStack networking project, was to enable tenants, enable users to create complex network topologies based on the needs of their applications. And we've, over the years, we've placed a lot of emphasis on that. So essentially, we provide you with a toolkit with different components to create whatever network topology your application requires in the cloud. Another important thing that Neutron has been able to do over the years is that we enable the admins of the cloud, the administrator of the cloud, to create a complex layer to provide a network topology. And provide a network meaning the network defined by the administrator that indicates how that network is going to be realized physically in the data center. So essentially, we enable the administrator to create a complex topology in terms of segments. A network can encompass many different segments, and each one of those segments can be of different technologies. You can mix physical VLANs with VXLANs and stitch all that together in a single unified level 2 network, unified broadcast domain. And what is important to mention here, point out here, is that ports are associated with the network, not with the segments. So your ports can communicate with each other independently of what segment in the network they reside at. So that was the emphasis in Neutron for many cycles. And then over the past 3 or 4 cycles, the question kept coming more and more. What if some tenants and some users, and in some use cases, it's not that important to have all that rich toolkit for tenants and for admins to create these complex network topologies? What if in certain use cases, the emphasis and the importance is really on just providing a port to the VMs, and they want to have a large number of VMs connected to those networks? Of course, one alternative is to create a large layer 2 network, but that has its downside. It essentially creates a large failures domains. It becomes difficult to scale from the point of view of performance. So the community more and more concluded that having this large unified broadcast domain was not necessarily the best approach in this specific use case where we want to have a large number of ports in the same network and supporting a large number of users. And of course, another alternative, if your use case is that and you want to achieve this level of scale, is that you can have define several networks and have your tenants, your users to select from a number of different networks that essentially provide the same service. The downside of this is that this leaves the choice of which network to select to the user. Each user, when they use the network, the cloud, they essentially have the task of defining where they want to connect, and that's not necessarily the most optimal approach because it can create confusion because essentially nothing distinguishes one network from the other. So the community sat down. We worked we worked for some time, and we came up with a routed networks approach. And in the routed networks approach, essentially what we said is that on top of having the traditional L2 networks in Neutron, we are going to have the concept of routed networks. And a routed network is really a number of segments, physical segments in the network that are they don't necessarily belong in the same broadcast domain. We are going to keep them separate, and we are going to allow the users to create ports and connect VMs to these different segments. And the way we are going to stitch together this collection of segments in a single network is that we are going to provide a routing function. And that routing function is really not provided by Neutron. It's provided by the infrastructure of the deployer. The deployer has to provide the means of routing the different routing the different segments in the network and stitch them together in a unified network. This allows for simplicity, and really the emphasis here is to provide simplicity and scalability at the same time. So in this manner, what happens is that now the users can have, these users who only want a port to a network, they can have a big, large network where they connect. We can achieve a scale without necessarily providing them with different confusing alternatives to select their networks. So how we implemented this concept? Essentially, prior to this effort, we already had the concept of segments, obviously in Neutron, and we had an API that was deep in the DV layer of the reference implementation, and we took that concept and we created an extension and a service plugin to enable the users to directly create segments through an API extension. And what is important to remember here is that a segment represents has a network type. It can have a segmentation ID associated with it, and it can have a physical network associated with it. We are exposing this as a service plugin, and that's implemented with ML2, and also in OVN they have access they use this to be able to create segments. And the other thing that we did was to create a segment host mapping in the database. Now it's important to know since the networks are not necessarily a contiguous L2 domain, it's important to know exactly what segments can be accessed from what host. So we can stitch this together. And we'll see that a little more detail in forthcoming slides. So this is more or less a simplified vision of what a routed network looks like. Essentially, we have a number of racks, and each rack has its own segment, and those segments are stitched together in a single network with a router. Again, that router is not part of Neutron, it's part of the infrastructure and has to be provided by the deployer. So how do you create a routed network? Essentially, you create a routed network when you create a network. When you create a network, essentially, by default, it's an L2 network. But when you when you create a subnet in that network and you assign a segment to that network, and at that moment, by definition, that network becomes a routed network. Because what's going to happen is that each segment is going to have, if we go back one, each segment is going to have its own IP range. And as a consequence, in this scenario, networks have a new attribute, the L2 adjacency attribute. And essentially what that means is that it tells the user whether this network all its segments are adjacent or not. In the beginning, when you create a network, this attribute is true. But then when you assign a subnet, a segment to a subnet, that attribute becomes false. Because now, this network is not anymore a contiguous L2 domain. And the other thing that we did in implementing this is that obviously each segment is going to require at least one DHCP server, so ports can get their IP address. So at least in each one of these segments, in this case, at least in each one of these racks, you need to have one DHCP server somewhere in that rack. So when we create ports, those ports can get their IP addresses. So what's the implication of this for the creation of ports? When you create a port in a routed network, what happens is that if that port is not bound, you cannot assign an IP address because you don't know where in which segment and therefore in which IP range that port is going to reside. So when you create a port, essentially, if you don't bind that port immediately, that port is going to become deferred. It has an IP allocation attribute, and the value of that attribute is going to be deferred because the port has been created, the port exists in the database, but we don't know yet where that port is going to land. And what's going to happen is that we bind that port. At that point is where we assign an IP address to the port. So all of this was implemented, as I said, a couple of cycles ago, and it's been there in the repo over the past 2 cycles. And the next step is that now we want to be able to assign floating IPs to those ports that reside in a routed network. And essentially what that allows us to do is to be able to enable those ports to go outside the cloud. And to do this, the approaches that we are going to be using BGP. We have a associated project to Neutron that it's called BGP Dynamic Routing. And essentially what we do there is that with a BGP speaker, we advertise the next hop for the physical routers in the infrastructure to know where the floating IP resides. Because we are going to take that floating IP, we are going to assign that floating IP to a port in one of those segments, and the routing infrastructure needs to understand where to send the traffic that is directed to that floating IP. And we are going to use DVR to enable routing neutron, the NATing of those floating IPs inside neutron. So at this point.
So I think everyone might be aware about the DVR architecture by now. So what we thought is for assigning floating IPs, since DVR is already distributed and has, in most of the cases, it has external network connectivity from the compute host. So it's basically easy to assign a floating IP to a port which is already bound. So I stress the word bound because DVR kind of works only with bounded ports. So basically, when you are assigning a floating IP, make sure that the port is actually bound to a host. So in the case of routed networks, it is already assumed that the port is actually bound to a particular host. So there is no issue with respect to floating IP getting assigned and configured with respect to the DVR routers. So what we can do is, here we actually have a kind of, in the DVR case, we can have a pseudo router where it just does the DNAT part of it because all the routing is being provided by your external network. The option that we are giving here for the segment is to forward the traffic, DNAT it, and send it out. And then when the traffic comes in, it actually sends it inside the VM and gets it out. So in our case, we already have a FIP namespace that you already have seen in DVR. So each and every compute host will have a FIP namespace. And each FIP namespace has a gateway port, which is an IP address that is being consumed from the public IP address. So in the case of routed networks, the public IPs are provided by an external network, which is not actually governed by Neutron. And in the same case, we don't want to consume too many IP addresses from the public. That was a concern for DVR for a long time. And I think that is the reason that we introduced the concept of service subnet types. So I think it was introduced 2 cycles back, the service subnet types. If you don't want DVR to consume a public IP address from your external network, what you can do is you can actually create a service subnet type with a private IP scope. And then you can use that for the FIP agent gateway ports to consume the IP addresses from that subnet so that you're not consuming any of the public IP addresses. All you're doing is the gateway needs an IP address and you are providing a private scope for it. And then with that private IP addresses and with the combination of BGP, we should be able to advertise where these floating IPs are residing on which compute host and then go back and forth. So, so this is a general outline of the DVR. Let me go into the details about the the service subnet types that I just discussed about. So in this case, the pink line that you're seeing is basically the packet flow path for the floating IPs. So when you have floating IPs assigned to VM1 or VM2, so assuming in this case VM1 is on one subnet segment, and then you assign a private IP address and you assign a floating IP, your traffic actually flows through the BREX, which is basically an external connectivity to your external network. So this is how the DVR works today. And if you look at the internal aspects, as some of you may be aware about it, it has a QR namespace and a FIP namespace. Basically, the FIP namespace is being shared between multiple tenants. And then you can have multiple queue routers on a same compute host, but you can only have one FIP namespace. So the FG port that I just talked about, which consumes an IP address, is basically this port, which consumes an external IP address. So that is where we are trying to tackle this issue, where we don't want it to consume an IP address from an external subnet, so we can actually provide it through a service subnet type, and then advertise the next hop using the BGP routers. So, so this is just a summary of what I just discussed about. So DVR consumes one external IP address. This is just a notes for someone who wanted to take it. But I think basically I have just spoken about those things. So in the case of defining a subnet type, service subnet type, so here's the commands that you basically use to create a service subnet type. So what you normally, in a Neutron case, you create an external network, and then you assign a subnet to an external network. And then if you don't do anything, it's going to consume IP addresses from an external subnet. But in the case of, in this scenario, what you can do is you can create a subnet range just for the external subnet. In this case, it can be your external routed network subnet that you are going to provide. And then in the case of floating IP agent gateway port, you are providing another scope, a private scope, which is being basically used internally, and it's not going to be exposed outside. So you're not consuming an external IP in that case. So once you do that, after you configure a gateway for your routers, so once you configure a gateway, you basically get a floating IP agent gateway port created on all the compute hosts that you're having where the service is being provided for a VM. And if you look at the FIP agent gateway port, the port details will tell you it has consumed IP address from the IP range that you allocated using the service subnet type. So now let's go into the details of what I just discussed, okay? So here in this picture, if you're seeing, you're seeing the green segments of the VMs that are in segments connected together. And you're seeing the 10.10 address is your private IP that your Neutron provides for your VMs. And the floating IPs are consumed from the public IP that you just created, which is 203.0.113, which is basically the external router that you have. And then you created a service subnet type with the 192.168 address. That's where the FIP agent gateway port gets an IP address from. So all those service subnets are having 192 scope, so it's not going to consume any IP addresses from the public, so it's all private. But the BGP speaker, as Meguls mentioned, so we have a project called BGP that has been released like 2 cycles back, and we can actually basically use the BGP speaker to monitor the networks that it has to monitor and advertise the routes. So BGP can then monitor those 2 networks, and then it can say, tell the router, okay, where is this floating IP coming from? This 22 is actually residing in this node, so your next hop is going to be that guy. And then based on that, your traffic will actually go in and come out. So one thing we may have to probably take into consideration is if there are any security rules that you wanted to apply for the queue routers, you wanted to get rid of that because all your routing is going to be done outside. You don't want to do any kind of security issues inside the Neutron space. So that has to be handled in the case of routed networks. Otherwise, the traffic will actually flow through this one with the help of BGP. So again, the key aspects for this one to be used is basically we need a BGP speaker, we need the service subnet types to be defined, and then the providers can actually use an external router to route the traffic. So again, DVR also has a concept of the direct path access, which is basically if you don't have floating IPs, this is not directly related to the routed networks, but in case if you don't have floating IPs, if you don't want to have a floating IP, you want to send the traffic directly outside, expose your internal private subnets to your outside world. So in that case, it's all governed by the address scopes because Neutron also has the concept of address scopes and subnet pools that you can define. So if your external network and internal network are on the same address scopes, DVR with the same concept without doing floating IP, it can actually send traffic back and forth from the compute host. So back to Megul now.
So thank you, Swami. So the next step in this implementation of functionality is this has an effect on the scheduling of instances in Nova. When you create an instance, that you can have Nova create the ports, or you can create your port and provide that port to Nova, so it can create your instance. But now the problem is that Nova doesn't necessarily is able to dispatch that instance for execution in whichever in any random compute host, because if you create a port and that port has an IP address, then that port needs to land in a compute node where that IP range is available. So there's a work being in Nova. As you may be aware, there's a big initiative on the Nova side that is called the Placement API. And essentially, the Placement API is a way where you can influence the working of the scheduler in the selection of the compute hosts where your instance is going to land. In relationship to Aurora Networks, essentially we identify 4 different cases. If you boot with a port IP and the port has no IP address, any segment with available IP addresses is good for that instance. But if you identify a port, if you create your port and your port has an IP address, then the segment with a subnet containing that IP address, that's where your instance has to land. If you provide a network ID, again, any segment with available IP address is good. And in the case of moving an instance, you have to move your instance that contains the segment with the IP range where that IP address belongs. So in the Placement API, there's this slide shows the main concepts, the main constructs that exist in the Placement API. And essentially what you do is you define resource pools. You tell the Placement API, I want to have this resource pool, and that resource pool has these inventories. In other words, resources, an inventory of resources that can be allocated by Nova using the Placement API. And then you have aggregates, which is a collection of hosts that are related to those inventories. How do we transform that, or how do we use that in the case of routed network? Well, essentially what we are doing is that when you create a segment, and that segment is associated to a subnet, we create a resource pool. And we associate an inventory to that resource pool with the IPv4 range for that segment. And then we associate with the aggregate of that resource pool the different hosts that have access to that network segment. And in this way, when you create your instance, what's going to happen is that the scheduler is going to use this information through the Placement API to select the host where your instance is going to land. And essentially, what we are trying to make sure is that when you create an instance and that instance lands in a compute host, it has IPv4 addresses available to it, and that are reachable within the segment that is associated with that compute host. This is work in progress. I understand that Nova is going to be able to consume that at the end of the cycle. Would that be fair to say? Or we don't know yet. Okay. But from what needs to be said is that from the point of view of neutron, this functionality already exists. We are already using, if you deploy a router network and you start using that, Neutron is going to be creating this information through the Placement API, and it's every time you create a port, every time you assign an IP address, that information is updated through the Placement API from Neutron.
So we have 5 minutes, I think.
Okay. So In terms of configuration, well, essentially, if when you want to deploy router networks, you need to identify your segments with your physical nets. You need to assign VLAN numbers that are associated with those physical nets. You need to create a DHCP agent host per physical net, per segment, and then you need to provide the physical routing, your choice of routing architecture. So you configure your segments using the service plugin. You provide in your configuration the bridge mappings for your physical networks. You create your network, and you associate to that network subnets where a segment is associated to it.
I think those are backups.
Yeah, this is backup information. So that pretty much covers the update that we wanted to provide today. It's important to say that out of all this functionality, the routed networks functionality is already implemented, it's already in place. The floating IP extension, that's what we are working currently on the Neutron side, and we are seeing when the placement information that is being sent to the placement API can be consumed by the Nova schedule.
I think the floating IP work that Miguel mentioned is basically with respect to BGP right now. Most of the DVR work is already in place, but we need to make sure that, because currently the BGP speaker just speaks to the centralized network node, so we need to make sure that the BGP speaker identifies the floating IP agent network ports and service type networks, and then advertises the routes.
So that was the information that we prepared for you guys. So let's have a Q&A.
Thank you, Sonny. Thank you, Miguel. Actually, the routed network is exactly the use case that I have in mind. And unfortunately, because Nova didn't quite catch up with the features in Neutron, we had to monkey patch it and adapt it in our own way to do the same thing. So basically, we did like runtime network ID replacement kind of hack. But you said, of course, it's not your scope, and you don't understand when it's going to be implemented in Nova. You said it's going to be now, it's going to be rocky or whatever. But is there any other way to use it from Nova in its current state?
No.
So,
There's
the deferred port thing is that went into Nova in Newton. It doesn't use placement at all. It's just provide a deferred port, and then it gets an IP when it's bound in the queue. There's no intelligent like scheduling involved in any of that.
so I just create like deferred port or provide a deferred port, but when it gets bound, it's how it gets bound.
So what's going to happen is that if you are careful if you are careful in your use case and make sure that your users don't pass a port with an IP address associated with it, it should work. Because essentially what is going to happen is that you're going to create your instances in Nova. Nova is going to create the port for you, and we can select at that point any segment in the router network, and it should work. So the functionality is usable in a restricted manner.
Less control manner. So is this from Newton? Okay.
But like when you move that instance that is now bound to the source host,
No, that's another story.
when you move it, the Nova scheduler has no idea that it needs to be restricted.
Right.
To the same segment.
Right. So that's why I say the functionality is going to be available as long as you're careful that certain things don't happen in your
With certain precaution, I might even try this.
exactly, with certain precautions.
Another question.
Sure.
Is this usable in any way in bare metal?
No. It's for VMs really.
So that's something that might be a next step for implementing. What organization are you with?
Line Japan.
Okay.
So what's the use case in the bare metal scenario that you talked about?
Basically, same, like we have segregated racks by VLANs.
So you wanted to provide networkings for the physical infrastructure.
Same way that we provide VPNs, we want to provide to physical machines.
Okay.
So let's have this conversation again, probably next week.
Okay.
I want to explore this.
Okay.
Yep.
Thank you very much.
All right. Very welcome.
Anything else?
If the actual status of, there was the one slide that said we were going to move the port creation out of the compute and then the conductor. That was something that the OSIC team was working on back when there was OSIC. And then there wasn't OSIC. And so there's a bunch of like merge conflict code that nobody's working on. So if you want the honest answer to like what the status of this is and the Nova side is, there's nobody working on it. There are people working on stuff with placement in the scheduler, but it's not specific to like the port use case. So, like the people as developers, you know, money up. But
Well, this is kind of news to me. I didn't really know about this side of the story in Nova. So it looks like something that somebody actually might take over.
and the moving of where we do the port creation, the conductor also has implications for another feature, which is bandwidth aware scheduling. So that's a whole other like feature that people want to do is instead of all this bandwidth policy stuff on the Neutron side, and then Nova should use that to figure out where to put things. But we have to do all this like other work first. So
Yeah, I'll appreciate if you can escalate this into communication about where to continue.
yeah, I've got the project update this afternoon, so I don't know how much I'll bring it up yet.
Thanks.
So you have the Nova and the Neutron core talking to each other,
Well,
team leads.
I use both, so whether I don't know the communication details, I have to figure out how to put these things together.
Yeah, I think if you have a specific use case, as Miguel mentioned, like just bring it up and then maybe create an RFE for that as a bug RFE first initially, and then we can actually scrutinize it and then go forward.
Yeah. So the other thing that I want to mention is that there's a spec in for the floating IPs piece. So if you can provide feedback to that, it will be greatly appreciated. Yeah. Yes.
For the BGP speaker with the floating IPs, what's the mapping of that between either, I guess, the region or the tenants? Is there multiple instances of that for different tenants, just to, I guess, reduce some of the failure domain for that component, or how is that the availability of that considered?
So you have each tenant creates its own BGP speaker.
And then it's based on what you add to the BGP speaker as a network or subnet that you wanted to monitor.
Yeah.
So it's tenant basic.
Yeah, and part of the work that is being done right now is that we need to make the BGP speaker more intelligent in the sense to be segment aware. Because originally that wasn't the case.
Question. Does the BGP speaker at all deal with autonomous zones? Or is it only a virtual concept within this group but has no reference to the rest of my data center?
It's a virtual concept in this.
Is there any intent to try to make a BGP client that would actually be able to integrate with the rest of my data center?
Not that I am aware of. But again, that's something that we might consider. Yeah.
Anything else? Okay. No
Thanks so
more
much.
questions. Thank you, guys.